June 6, 1944. The largest amphibious invasion in human history crashes onto the beaches of Normandy, but even as the first waves of American, British, and Canadian soldiers fight their way inland, a clock is already ticking. Every infantryman storming those beaches needs ammunition, every tank needs fuel, every wounded soldier needs medical supplies, and every single ton of that material must come across the English Channel. The German High Command knew this. They knew the Allies would need a major port to sustain an invasion. That's why they fortified Cherbourg, Le Havre, and Calais with concrete bunkers, naval mines, and entire divisions of troops. Adolf Hitler himself had issued orders. The ports would be held to the last man. If they fell, they would be demolished so thoroughly that the Allies couldn't use them for months. The Wehrmacht's strategy was brutally simple. Let the Allies land, then strangle their supply lines and watch the invasion collapse. But on the morning of D-Day, something was already moving across the English Channel that would shatter this assumption entirely. Something so audacious, so unprecedented, that when Winston Churchill first proposed it in 1942, his own military advisors called it impossible. The Allies weren't going to capture a port. They were going to build two entirely new harbors in the middle of the ocean, tow them across one of the world's most treacherous stretches of water, and sink them off the coast of Nazi-occupied France. This is the story of the Mulberry Harbors, the most ambitious engineering project of World War II, and the one unsung innovation that made victory in Europe possible. To understand how this impossible idea became reality, we need to go back to the spring of 1942. The Allied invasion of Europe was still a distant dream, but military planners were already confronting an impossible mathematics problem. To land an army in France large enough to defeat the Wehrmacht, they would need to deliver approximately 12,000 tons of supplies per day. Within weeks, that number would need to grow to 20,000 tons, then 30,000. The logistical requirements were staggering. Every modern military operation in history had relied on capturing enemy ports intact. The Allies had learned this lesson the hard way. In August 1942, British and Canadian forces launched a raid on the French port of Dieppe. It was a catastrophe. Of the 6,000 men who landed, more than half were killed, wounded, or captured. The Germans had turned every harbor on the French coast into a fortress. Worse, Hitler had issued his demolition order. If the Allies somehow managed to capture a port, German engineers would destroy it so completely that it would be unusable for months. The British Vice Admiral John Hughes Hallett had been at Dieppe. He had watched men die on those beaches while naval vessels sat helplessly offshore, unable to deliver the heavy weapons and supplies needed to break through German defenses. After the disaster, he wrote a single sentence in his report that would change the course of the war. If ports are not available, we may have to construct them in pieces and tow them in. Winston Churchill read that line, and his mind ignited. Churchill had always been fascinated by engineering solutions to military problems. During World War I, he had championed the development of the tank. Now, in his cramped office beneath London, he scrawled a memo to his Chief of Combined Operations, Lord Louis Mountbatten. The memo was dated May 30th, 1942, and it laid out his vision: piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. Churchill's vision was audacious beyond measure. He wanted to build artificial harbors large enough to handle the same tonnage as the port of Dover. These harbors would need to protect ships from the English Channel's notorious storms and 20-foot tides. They would need to be built in England, towed across the Channel in pieces, and assembled off the coast of France while under potential enemy fire. And they would need to be operational within days of the invasion. The British Admiralty thought Churchill had lost his mind. Naval architects said it couldn't be done. The tides alone made it impossible. The English Channel experiences some of the highest tidal ranges in the world, with water levels rising and falling up to 20 feet twice a day. Any fixed structure would be submerged at high tide or stranded in mud at low tide. Any floating structure would be smashed to pieces by the channel's storms. But Churchill didn't care about impossibility. He cared about necessity, and the necessity was absolute. Without ports, there could be no invasion. Without an invasion, Nazi Germany would control Europe for a generation. The task of turning Churchill's impossible vision into reality fell to a 42-year-old civil engineer named Hugh Iorus Hughes. Hughes was a quiet, methodical man who had spent his career building dams and bridges, not military installations, but he possessed something rare among engineers, the ability to think at a scale that bordered on the absurd. Hughes's solution centered on enormous hollow concrete structures called caissons. These would be the foundation of everything. Each caisson, code-named Phoenix, would be a floating concrete box, 6 stories tall and as long as a city block. They would be towed across the channel while still floating, then deliberately sunk in position to form a breakwater, an artificial barrier that would calm the waves and create a protected anchorage. The numbers were staggering. Each Phoenix unit would weigh up to 6,000 tons. The walls would be 6 feet thick to withstand the channel's brutal wave action. Inside, they would be divided into chambers that could be flooded with precise control to sink the structure level and stable. The largest Phoenix units would be 200 feet long and 60 feet tall, as enormous as a battleship turned on its end. But the caissons were just the beginning. Hughes designed an entire artificial harbor system. Floating roadways, code-named whales, would stretch from the shore to the deep water anchorage. These roadways would flex with the tide, rising and falling on steel pontoons. They would be strong enough to support loaded trucks and tanks, yet flexible enough to bend with 20-foot tidal swings. The roadways would connect to spuds, enormous steel-piercing legs that would be driven into the seabed to anchor the entire structure. The project required resources on a scale that beggared belief. The concrete alone needed for the Phoenix caissons would require 330,000 cubic yards, enough to build a highway from London to Birmingham. The steel requirements were so enormous that they competed directly with the production of tanks, ships, and aircraft. At a time when Britain was still rationing food and fuel, Churchill was demanding that they build 2 entire artificial ports. Construction began in secret in the summer of 1943 at sites scattered across the British coast. At Southampton, Portsmouth, and a dozen smaller harbors, enormous dry docks were constructed specifically to build the Phoenix units. Each caisson took months to build. Concrete had to be poured in precise layers, allowed to cure, then poured again. The structures were so large that they created their own microclimates, with temperature differentials inside the forms that could crack the concrete if not carefully managed. The workers building the Phoenix units had no idea what they were creating. Security was absolute. To anyone watching, they appeared to be building enormous concrete boxes with no obvious purpose. The rumor among the construction crews was that they were building underwater oil storage tanks, or possibly submarine pens. No one suspected they were building portable harbors. By the spring of 1944, the British coast was lined with these mysterious concrete giants. In the Thames estuary alone, more than 30 Phoenix units sat in the water, tethered like enormous silent ships. Each one had been fitted with anti-aircraft guns and minimal crews. They sat low in the water, barely clearing the waves, waiting. The Phoenix caissons would form the outer breakwater, but the Allies needed additional protection from the Channel's ferocious weather. The solution was Operation Corncob, one of the most bizarre naval operations in military history. The Allies would deliberately sink an entire fleet of ships to create an inner breakwater. The ships selected for this mission were called gooseberries. They included 74 obsolete warships and merchant vessels that had been stripped of anything valuable and prepared for scuttling. Among them were ancient Great War battleships like HMS Centurion, her guns removed, her armor plating weakened with carefully placed explosive charges. There were rusted freighters that had survived U-boat attacks only to be marked for this final mission. There were even captured enemy ships, including a former French destroyer. Each gooseberry ship had been carefully prepared. Explosive charges were placed throughout the hull, designed to blow out the bottom plating and settle the vessel evenly on the seabed. The ships would be sailed to their final positions by skeleton crews, then abandoned and sunk in precise formation to create a continuous barrier. The men selected to crew these doomed vessels knew the risks, though their mission was less dangerous than it appeared. They would sail the ships across the channel on D-Day itself, under the cover of the invasion fleet. Once in position, they would set the scuttling charges, evacuate to small boats, and watch as their vessels settled into the seabed. But the gooseberry ships were just one layer of the harbor's protection. Beyond them would come the bombardons, enormous floating steel cruciform structures that would float on the surface and break up incoming wave action before it reached the harbor. Each bombardon was 200 feet long and floated at an angle, designed to let waves roll over them while absorbing their energy. The entire system, when combined, would create a protected anchorage capable of sheltering dozens of vessels. But none of it would work if they couldn't get it across the channel. On June 6, 1944, while the world's attention focused on the soldiers storming the beaches of Normandy, the most unusual naval convoy in history was leaving the British coast. The first Phoenix caissons were under tow, moving at barely 3 knots through the choppy waters of the English Channel. Each Phoenix was pulled by multiple tugboats, sometimes as many as 4 or 5 for the largest units. The caissons rode low in the water, their decks barely 10 feet above the waves. In calm seas, the crossing would take nearly 20 hours. But the channel was never calm. The crews aboard the Phoenix units faced a unique terror. They rode on structures that were deliberately designed to sink. If something went wrong during the crossing, if a seam split or a storm surge flooded a chamber, the Phoenix would go down in minutes, taking its crew with it. There were no lifeboats that could be launched in time. The men manning the anti-aircraft guns and monitoring the ballast systems knew that their concrete island could become their tomb at any moment. Some Phoenix units never made it. The Channel crossing of June 1944 encountered weather that, in any other circumstance, would have halted all naval operations. Winds gusting to 30 knots whipped the channel into a frothing chaos. Several Phoenix units broke their tow cables and began to drift. Crews aboard the runaway caissons fought desperately to reestablish tows, while their concrete fortresses wallowed in the swells, each wave threatening to flood the ballast chambers and send them to the bottom. At least one Phoenix unit began taking on water during the crossing. The crew watched in mounting panic as water poured through a crack that had opened in the concrete wall. They worked the ballast pumps at maximum capacity, but the Phoenix was settling lower with each passing hour. Finally, with the French coast barely visible on the horizon, the order was given to abandon. The crew scrambled into small boats and watched as their Phoenix, containing tens of thousands of hours of labor and thousands of tons of concrete, slipped beneath the waves and vanished. But most of them made it. Over the course of 2 weeks, 213 Phoenix units were towed across the English Channel. It was the largest movement of concrete structures in human history. From German observation posts on the French coast, the sight must have been surreal. Enormous concrete monoliths, each the size of an apartment building, creeping across the horizon in an endless procession. Behind the Phoenix units came everything else. The whale roadway sections, each 200 feet long, were floated across in chains. The spud pier legs, Enormous steel structures, weighing hundreds of tons each, were towed on specially constructed rafts. The bombardons came in sections to be assembled off the French coast. More than 600 tugs and towing vessels were involved in the operation, pulling more than 400 separate floating components. Off the coast of Arromanches and Saint-Laurent-sur-Mer, British and American naval engineers began the most complex construction project ever attempted under combat conditions. They were building two harbors, codenamed Mulberry A and Mulberry B, while German artillery batteries still operated within range, and the Luftwaffe made sporadic bombing runs. The first task was sinking the Gooseberry ships. On the evening of June 7th, the first obsolete vessels were sailed into position. HMS Centurion, the old battleship that had served in the Great War, was among them. Her skeleton crew set the explosive charges, evacuated to waiting boats, and detonated. The charges blew out her bottom plating, and she settled into the seabed in less than 15 minutes, her superstructure still visible above the waterline. Ship after ship followed. They were sunk in a precise line, each vessel positioned so that the next would overlap slightly, creating a continuous barrier. By June 10th, the inner breakwater was complete. Behind it, the water was noticeably calmer, protected from the worst of the channel's chop. Then came the Phoenix units. This was the moment everything hinged on. Each Phoenix had to be positioned with extraordinary precision, then sunk in exactly the right way to settle level and stable on the seabed. Too fast, and the enormous weight of concrete would drive the caisson deep into the soft mud, possibly tilting it beyond recovery. Too slow, and the tides and currents would push it off position. The Royal Engineers developed a careful sequence. Each Phoenix would be towed into position and held by multiple tugs. Divers would go down first to examine the seabed, ensuring it was relatively level and free of obstacles. Then the flooding would begin. Valves deep inside the Phoenix would be opened in a specific sequence, allowing water to flood the internal chambers. The crews monitored the settling with levels and plumb lines, adjusting the flooding to keep the structure level as it descended. The process took hours. The crews aboard each Phoenix worked in agonizing tension as their concrete islands slowly settled beneath them. The first Phoenix units went down perfectly, settling level into the mud with only their tops protruding above the waterline. But others tilted during the settling, their enormous weight driving one corner deeper than the others. Engineers tried frantically to correct the tilt by flooding chambers on the opposite side, but once a Phoenix began to tip, it was almost impossible to stop. Several Phoenix units settled at severe angles and had to be abandoned as unusable. By June 15th, the outer breakwater was taking shape. From the air, it looked like an enormous concrete wall rising from the sea, arcing around the anchorage in a protective embrace. The Phoenix units stood in a line, their tops 10 to 15 feet above the water, creating a barrier nearly 2 miles long. On June 18th, just as Mulberry A and Mulberry B were becoming fully operational, the English Channel produced a storm of almost unprecedented ferocity. It would become known as the Great Storm, and it would nearly destroy everything the engineers had accomplished. The storm came up suddenly, as channel storms do. By mid-morning, winds were gusting to 40 knots. By afternoon, they had reached force 6 on the Beaufort scale, nearly storm force. Waves 20 feet high began hammering the artificial harbors. The timing could not have been worse. Many of the floating roadway sections were still being installed. Some of the Phoenix units had been sunk, but not yet completely secured. The bombardons, the floating wave breakers, had only just been towed into position. At Mulberry A, the American harbor at Saint-Laurent-sur-Mer, disaster struck within hours. The bombardons broke loose first, their anchors ripping free from the seabed. These enormous steel structures, each weighing hundreds of tons, became battering rams. They smashed into the whale roadways, tearing apart the floating pontoons. Then they struck the Phoenix units. The concrete caissons could withstand wave action, but they had never been designed to resist the impact of 200-foot steel structures slamming into them at the speed of wind-driven waves. Several Phoenix units at Mulberry A suffered catastrophic damage. Their walls cracked under the repeated impacts. Some began to list as water flooded through the breaches. The whale roadways were completely destroyed, their pontoons smashed and scattered. By the evening of June 19th, Mulberry A was a scene of devastation. Millions of dollars of equipment and tens of thousands of hours of labor were being ground to scrap by the channel's fury. The American decision to abandon Mulberry A was made quickly. The harbor was too damaged to save. Engineers salvaged what they could, towing undamaged sections south to Mulberry B. The rest was left as a twisted memorial to the channel's power. But Mulberry B, the British harbor at Arromanches, survived. The difference came down to two factors. First, Arromanches had slightly better natural protection from the prevailing winds. Second, the British engineers had been more conservative, taking extra time to ensure every Phoenix unit was properly secured before moving on to the next phase. When the storm hit, Mulberry B flexed and groaned, but held. The Phoenix unit stood firm. The whale roadways, though damaged, remained functional. When the storm finally broke on June 22nd, Mulberry B was still operational. The survival of Mulberry B would prove decisive. Over the following months, this single artificial harbor would handle more cargo than any natural port on the French coast. It became the logistical foundation of the entire Normandy campaign. From June through October 1944, Mulberry B operated 24 hours a day, 7 days a week. The harbor that military planners had called impossible became the busiest port in the world. The numbers tell the story. In the first month of operation, Mulberry B handled more than 200,000 tons of supplies. By September, that number had grown to more than 500,000 tons. Tanks rolled down the whale roadways. Artillery pieces were swung ashore by cranes mounted on the Phoenix units. Ammunition trucks drove directly from Liberty ships onto the floating roadways and then onto the beaches, without the cargo ever being exposed to the weather. The harbor could accommodate up to 20 Liberty ships at once, all simultaneously unloading. The whale roadways stretched nearly half a mile from deep water to the shore, flexible steel and concrete ribbons that rose and fell with the tides, but never broke. Engineers had calculated that the roadways could handle up to 10,000 tons per day. In practice, they routinely exceeded 12,000 tons. German commanders watched in mounting disbelief as the tonnage figures came in through their intelligence networks. They had assumed that the destruction of Cherbourg's port facilities, accomplished during the German retreat, would cripple the Allied advance. Instead, the Allies were receiving more supplies through their artificial harbor than Cherbourg could have handled at its peak capacity. Field Marshal Erwin Rommel, in his final reports before his forced suicide, mentioned the harbor specifically. He wrote that the German High Command had fundamentally misunderstood Allied logistics capabilities. The assumption had been that the Allies would be tied to captured ports, and thus vulnerable. The reality was that the Allies had freed themselves from that constraint entirely. They had brought their own port with them. By the time Mulberry B was finally decommissioned in November 1944, it had handled more than 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. Those supplies kept the armies in France fueled, armed, and mobile through the critical months when the Wehrmacht was still capable of mounting significant counteroffensives. Without Mulberry B, the Allied advance would have stalled. Divisions would have run out of ammunition. Tank columns would have run out of fuel. The timetable for victory would have been pushed back by months, possibly years. The story of the Mulberry Harbors is often told as a tale of industrial might, of Britain and America's ability to outproduce the Axis powers. But that misses the deeper point. The Mulberry Harbors were a triumph of imagination over conventional thinking. When Hughes and his team of engineers first began designing the Phoenix units in 1942, they had no blueprints to work from. Artificial harbors had never been built before on this scale. The largest floating structure ever constructed had been a floating dry dock, and that had operated in calm, protected waters. What Hughes was proposing was to create structures larger than those dry docks, then subject them to the full fury of the English Channel. The conventional wisdom said it couldn't be done. The naval architects were particularly skeptical. They understood ship design, and ships were built to flex and bend with the waves. Concrete doesn't flex, it cracks and breaks. The idea of building rigid concrete structures and expecting them to survive in the Channel seemed to violate every principle of naval engineering. But Hughes understood something the naval architects didn't. He understood that the Phoenix units didn't need to survive in the way a ship survives. They only needed to survive long enough to be positioned and sunk. Once on the bottom, the enormous weight of concrete would be their strength, not their weakness. The wave forces that would tear apart a floating structure would be largely dissipated by the time they reached the anchored, sunken caissons. This insight, simple in hindsight, was revolutionary in 1942. It required thinking about the problem in an entirely new way. Not as a ship that needed to float, but as a temporary floating platform that would transition to a permanent anchored structure. The same kind of lateral thinking ran through every aspect of the Mulberry design. The whale roadways were another example. Conventional piers were rigid, built on pilings driven deep into the seabed. But the Channel's 20-foot tides made that approach impossible. A rigid pier would be underwater at high tide or stranded in the air at low tide. Hughes's solution was to make the roadways float, but connect them to anchored piers with pivoting joints that allowed the roadways to ride up and down with the tide, while remaining horizontal. It sounds obvious now. In 1942, it was revolutionary. The strategic importance of the Mulberry Harbors becomes clear when you consider what would have happened without them. The Allied plan for Overlord, the D-Day invasion, assumed that Cherbourg would be captured within a week and brought into operation within a month. This timeline was catastrophically optimistic. In reality, Cherbourg didn't surrender until June 26th, 3 weeks after D-Day. When Allied engineers finally entered the port, they found devastation beyond their worst projections. The Germans had destroyed every crane, blown up every dock, sunk ships in every deep-water channel, and demolished the lock gates that controlled access to the inner harbor. The Allies estimated it would take 3 months to make Cherbourg operational. It actually took 6. Without the Mulberry Harbors, those 6 months would have been a logistical nightmare. The Allies would have been entirely dependent on beach landings, unloading cargo directly from ships onto the sand. This method, called drying out, was slow, weather-dependent, and wasteful. A single storm could halt operations for days, and the beaches couldn't handle heavy equipment. Tanks could be landed, but not artillery pieces weighing dozens of tons. Locomotives couldn't be unloaded at all. The result would have been a strangled advance. Allied divisions in France would have been perpetually short of ammunition, fuel, and replacement equipment. The Germans, though retreating, would have had time to establish defensive lines and bring up reinforcements. The most likely scenario is that the Allied advance would have stalled somewhere around Paris, with supply shortages forcing a winter pause in operations. This would have had cascading consequences. A pause in the west would have allowed Germany to shift divisions to the Eastern Front, possibly stabilizing the situation against the Soviet advance. The atomic bomb program, still months away from completion, might have been diverted to European targets instead of Japanese ones. The political landscape of post-war Europe would have been fundamentally altered. This is speculation, of course, but it underscores a critical truth about the Mulberry Harbors. They were not just a logistical convenience. They were the difference between victory in 1945 and a war that dragged on for years longer, with incalculable consequences. Today, you can still see the remnants of Mulberry B off the coast of Arromanches. The Phoenix caissons remain where they were sunk in June 1944, weathered by 80 years of tides and storms, but still standing. On low-tide days, tourists walk among them, marveling at these enormous concrete blocks rising from the sand. Few realize they are looking at the remains of the most important engineering project of World War II. The Mulberry Harbors proved a fundamental principle that would reshape military thinking for generations. Logistics is strategy. The side that can move more supplies, faster, to the point of contact will win. This seems obvious now. In 1944, it was a revelation. The German Wehrmacht was arguably the finest fighting force in the world on a tactical level. German tanks were superior to Allied tanks. German infantry tactics were more sophisticated. German commanders, on average, showed greater operational skill than their Allied counterparts. But none of that mattered when German divisions ran out of ammunition and fuel, while Allied forces could bring up supplies faster than they could be consumed. The Mulberry Harbors made that logistics dominance possible. They transformed the D-Day invasion from a precarious toehold into an unbreakable supply chain. They proved that engineering ingenuity could overcome geographical constraints that had seemed absolute. And they vindicated Churchill's initial instinct. When the conventional wisdom says something is impossible, sometimes the answer is to build the impossible anyway. Hughes, the quiet civil engineer who designed the Phoenix caissons, received a knighthood after the war. He deserved far more. The soldiers who stormed the beaches get the glory, and rightly so. But behind every one of those soldiers was a supply chain stretching back across the Channel, through the Mulberry Harbors, to the factories and farms of England and America. Hughes and his team of engineers built that supply chain from concrete, steel, and sheer audacity. The lesson of the Mulberry Harbors extends far beyond military history. They stand as a testament to what becomes possible when you refuse to accept the constraints others assume are immovable. When you're told something can't be done, sometimes the right answer is to ask a different question. Not how do we capture a port, but how do we build one? Not how do we make this structure survive, but how do we make it survive long enough? The Phoenix caissons still standing off Arromanches are more than just concrete and rust. They are monuments to the power of reimagining the problem, and they are a reminder that sometimes the most important victories are won not on the battlefield, but in the minds of engineers who dare to call the impossible merely difficult.